Welcome, everybody. My name is Paolo Cassano. Welcome to the MGH brain-PBM clinic round. Today is October 31st, 2025. It's my great pleasure to welcome Dr. Ali Yildirim, Chief AI Officer at Niraxx Inc., also affiliated to Oxford University in UK. He's going to talk about AI and photobiomodulation from QEEG-Guided neuromodulation to personalized brain stimulation. Welcome, Ali, and please take it away.
Thank you very much for a nice introduction, Paolo, and thank you to give me the chance to speak over here. I'm going to try to share my screen. Can you guys see the slides?
We can.
Okay, I can't see anything. If you can shout if anything happened, would be great.
No worries.
Thank you very much, Paolo. Yes, I'm going to talk a little bit about artificial intelligence and photobiomodulation. It's very interesting. It's Halloween day, and for some people, AI is a scary thing as well, but I'm going to try to explain more in details. Let me try to move. Some conflicts of interest. I'm working for Niraxx, Synkwell, and Deep Synapse, and also for Cosmos Health. On this presentation, we might sometimes mention different company names, but these are all the work we are doing over here. We're going to focus on the introduction to the AI. What is AI? What sort of type AI we've got, and also neuroscience. And we're going to focus on QEEG, personalized brain stimulation, some of the PBM evidence which we found out with AI, and how we implement them on Niraxx. And also, if we got some time, I'm going to focus on a little bit on biophotonics and quantum, and how AI field can learn from photobiomodulation and neuroscience field, basically. What is AI? AI is a system that tries to mimic human intelligence. As probably most of you guys are expert on human intelligence, how the brain work, and so on and so forth. AI people, they just try to mimic that into the more machine world, let's say. And there are three types of subfields on AI, basically. We've got machine learning, which is an algorithm that learns from data. Basically, if you compare this with the human learning, it's how machines gonna learn from the data, like how humans learn from the experience. Deep learning is, if you think like human intelligence, deep learning is probably same as our neural networking on our brain, different networks working with different part of the brain to process the information. Same as AI people, they just try to copy that in this deep learning model. Natural language processing, it's the quite popular one currently because of the ChatGPT and other large language models. Basically, formation to understand human better with the text, let's say. And for the first time, humankind got some sort of ability to use their own language to communicate with animations. Before, you need to know some sort of programming language to do that, but it's get democratized now. Most of the people around the world, they can use their own language to communicate with the machines, which is going to change most of the stuff, I think. Computer vision is like a vision of the AI, let's say. It's eyes of the AI. It's just process images and videos. And there are other parts as well, which we're going to mention later on. There are three pillars on AI: data, algorithms, and compute, like our brain. We're going to we're gonna mention them in details later on. Why everything getting popular now? Because of the technology, because of the data. We use lots of different apps and softwares. These are all collected lots of data. Now we can get some sort of meaningful explanation of different data sets. That's why it's getting popular. Also, hardwares like GPUs, TPUs, which is getting more affordable as well. AI, as we mentioned, try to mimic the human, try to mimic the learning, try to mimic the speech, text, vision, and so on and so forth. And then for each, they've got, like for the vision, for example, you got computer vision or object detection, and there are different models. For the machine to learn, there are different models under that as well. It's quite a broader topic, as we're going to mention now. As you can see, large language models in the core part in the middle, most of the people, most of the generic people, general public, when they mentioned AI, they are mentioning large language models. Large language models is just one part of the AI, but you got generative intelligent, general artificial intelligence, or some people call this AGI, which we're going to discuss a little bit in details. And you got deep learning, machine learning, all of them under the AI, which means that artificial intelligence. And there are, as human intelligent expert, probably you guys gonna think that how this machines can be act like human. I think there are some issues on definition of AI which need to be discussed further, because when you call intelligent on human, it's a more broader and holistic explanation. It's not just information processing. Current AI or machine intelligent, whatever you call it, is just processing information or doing little bit reasoning, but still there are lots of missing parts to get a real intelligence. The reason to do that, I think it's basically because of most of the engineer guys try to define AI rather than human intelligent people done that. That's why we need neuroscientists and neurologists or brain scientists to get involved and to explain how human intelligence work and how we can copy that to the machines, basically. Yeah. There are three types of AIs. One called ANI. It's a artificial narrow intelligence. This is basically a task-specific intelligence. Let's say you got a large language model for medicines, you got some algorithm for law or neuroscience or genetic or biology or physics. It's like, your temporal lobe of your brain just processing sounds or auditory information. And NI, like INI, is basically that specific AI. And AGI is like a general level of intelligence, which is going to be on the human level, let's say. Basically, AGI is like your brain, or human intelligent level intelligent. And there are some people, experts, they are claiming that we're going to get AGI in a couple of years. But yeah, it's not there yet, if you ask my opinion. ASI, it's super intelligent. Artificial super intelligent is behind the human cognition. It's a theoretical frame, which means that the intelligence is gonna be better than human. For super intelligent, currently there is no signs of it, because all this AI developments coming to a barrier, which is energy, memory, and information processing, which we're going to discuss in later slides. To getting super intelligent, we need to use a different model to process information much better and use that as well. There are a couple of candidates for that. One, quantum computers. and the other one is photonic computers or photonic approach, let's say, which is using light to process information, which we're going to touch by the end of the slides. This is the evolution of the AI. Basically, simple AI language started around 1960s, and then it's getting a little bit popular around 1980s with some, machine learning algorithmic works. And then, as you can see, machine learning starting over here as well. And then around 2010, with GANs and other transformers and neural nets, it's getting more popular. And with the COVID, I think we've got lots of data to process, and then it started to build up after 2020, let's say. And then currently, you can call this period around this 10 years, this decade seems like an AGI decades, but still not there yet. How are we going to use AI for neuroscience and neuroscience for AI? These are like two, like a mirror neurons, let's say. It's just one part is how we're going to use AI to provide better services to the people related to brain, and also how the brain science can help AI to be much better as well. It's just win-to-win approach, I think. Generally, as you're gonna find out, lots of literature around the drug discovery or neuroimaging, radiology, or mapping of the synapse or BCI application. These are all related to AI methods which we are using on neuroscience. At the meantime, and AI people, they try to mimic the brains, try to understand the functions of the different neural nets on the brain, how people learn it, how human behave, and then how can we translate that into the machines. They use different bio or physical models to understand machines better, understand human brain better, to implement them into the machines. Oops, sorry. Yes, as probably most of us are clinician, we use scan or QEEG scans or MRI scan, fMRI scan, CT scan, whatever. But AI people call this data collections, basically. You collect data from brain, you collect data from body. I've put simple data collection methods over here, which you can use with everyday tools to get to understand your clients and patients much better, and use some of the AI models to get some sort of perspective. Today, we're going to focus on QEEG, because QEEG is one of the easiest way to scan the brain, to understand the brain, because it's more democratized now. You've got lots of softwares, devices, which you can just use for a couple of minutes to understand roughly what's going on in the brain. And also, you've got lots of different variables now, like smart rings, smartwatch, getting lots of valuable data from body. Then you can combine them to create some meaningful application. I've put a couple of examples over here for the dry QEEG headsets for human. There is no scan for the AI yet, but probably in the future we're going to see some of the AI scan as well. These are for the AI people. This is basically called data collectors for AI. And you've got VAT QEEGs. These are like caps. You put gels on the electrode and get data from brain, and then use different software to analyze it. These are, again, data collectors for AI. And these are different hardware sensors for biofeedback or for different purpose people use it. And these are all daily wearable technologies, getting data from body, understand the body. All this data directly go to the AI itself, and mission intelligence or missions try to understand human much better with these different data collectors, which we are currently using it. And that's why I put this from George Orwell, but change it a little bit to the AI. All data are equal, but some are more equals than the others. If you use data much better, you're going to get much better results, basically. And obviously, when you get data, you need to make this data to useful for the machines itself, to machine to understand this data. This data need to be cleaned. And obviously, AI can help to clean the data as well. Human can clean the data as well for AI to understand different patterns. How you clean the data? You use different approach to see different, parameters. But currently, there are quite good AI algorithm can clean the QEEG data, but still not on the human level yet, because of the complexity. We clean the data, we got the data from brain, we clean it, and then after the cleaning process, we do pre-processing, which means that we use different AI algorithms to focus on different aspects of the data and then try to get some sort of meaningful answer for us, and then put that into some classification and so on and so forth. I'm not going to go in details on this. You can find different softwares and tools to do that. And then you can put this data on different visualization like this as a signal or topamap or Loretta, and with the exact localization as well, which are quite helpful. And different neuromodulation tools, they use them as a guidance nowadays. I've put ERPs over here, event-related potential. You can, while you are reading book, you can scan your brain. While you are riding horse, you can scan your brain and see how your brain working on that specific task. Most of the performance people use this. I think there are some sort of market for PBM for the peak performance as well. And also, when you do the scan, this is from iMedisync. You can get really good visualizations, and also you can see what's going on roughly on the brain. And this is an ADHD case. You can see theta beta ratios and see which part of the brain working on which frequencies and what is the consequences of it, and how can you manipulate or stimulate or change that specific part of the brain to get the result. There are lots of literature about the biomarkers for different condition with the QEEG, fMRI, MRI, and so on and so forth. I put a couple of them on the slide, but obviously today we are going to focus on more individualized approach. But vast majority of the literature you're going to see on depression, for example, going to mention that frontal alpha asymmetries or increased theta delta power, or on ADHD, you're going to see elevated theta beta ratios, reduced alpha or beta power, and so on and so forth. But obviously, these are all personalized as well. And in different persons, you're going to see different data patterns. I've done a quick AI-based literature searching, use a tool called Consensus. And Consensus got around 170 million research paper inside, and then it has some access to different databases, and we've done a quick research on the photobiomodulation in the brain or neuroscience, and we've got around 1,047 papers mentioning photobiomodulation related to brain, and we use different keywords as well. And then in this 1,000, we got 621 papers. In these 621 papers, we eliminate them and try to find top 15. These are all done by AI, and no human input on this. And then with this consensus tool, basically, and then we've put this top 50 papers, which is mentioning AI, and I'm gonna show you some of the results over here. Is photobiomodulation effective for neurological and neurodegenerative conditions? around 40 paper, 43, and you're going to see nearly half of it say yes, and the other half say possibly, which means that it's quite high. High quality animal and human studies, systematic review, meta-analysis, RCTs show that PBM have cognitive benefits. And also recently systematic review, narrative reviews, and others shows that there are more research needed for the clinical trials as well. But as you can see, PBM quite useful for the neurological conditions. These are the timelines for the published publications. Again, it's from consensus. As you can see, the publication after 2022 is getting higher and higher because of the AI technological change. I think maybe COVID, we're getting more publication now, and people use light to stimulate the brain more now, which is good. There are some claims and evidence table, which is coming from consensus again. PBM improve cognitive functions and neuroprotections in animal models is very strong, more than, I don't know, 10, 12 research mentioning that in this 15. PBM modulates mitochondrial functions and gene expressions, very strong evidence again. And it's again more than 10 paper mentioning that in this 15. PBM safe and well tolerant, again, it's a very strong evidence with a couple of paper mentioning that again. Clinical efficiency of degenerative diseases is promising, but needs some proven. It's moderate, and also the reason for that is there is very less large RCTs in there. Sorry, and these are other results. Why personalization in PBM matters? I mean, personalization in medicine is really important, and with AI, this is going to be a common practice, I think, which somehow we're going to get data from body and brain, and then we're going to find dose or related drug to target that specific part. For the PBM, again, current PBM, as you can see on the literature, is providing, if you got depression, you're going to use this. If you got sleep issues, you're going to use this. It's like one size fit for all. But with the AI and closed-loop applications, getting data from body and brain, you're going to see more personalized approach. You're going to give a protocol for depression in Ali. You're going to give protocol for sleep issues in Ali rather than general sleep issues protocols. And with the development in AI, I think you're going to see more research on there, and it's going to get more. There are some other evidence highlighting different aspects of the PBM, like wavelength or frequency or power density or mode. These are, again, different. In this 50 paper, we have seen on different condition what sort of wavelength they use and how this influence and density and so on and so forth. And we use this around 1,500 papers to train our algorithm as well for AI for PBM. How can we use AI for PBM? Basically, we're going to get data from body and brain, and then AI going to understand this data much better, and then AI going to advise the dosage, timing, and place, and so on and so forth. And then if it's going to be probably first couple of years, or maybe it's going to be more hybrid model, which AI going to find the places and dosage. Human doctors going to check that and then apply it. But when AI going to start to learn from it, and it might be we're going to probably in 5 or 10 years, you're going to see more automated approach as well. Like you're going to put a helmet on your head or a cap or just a basic wearables. It's going to get data from the body or brain, and AI going to modulate that and send relevant frequencies or lights or sounds or magnetic signals or electrical signals, whatever way you use to stimulate that part to get optimal level. But these are probably not far futures. How we are doing this application in Niraxx, we've created this textile-based neuromodulation headband. We've got 500 plus prototype headband sent it to people. We create an app called SyncWell, which is getting sleep, steps, and HRV data. It's a prototype app. Basically, when people use it, they can see their data, how their data changes on the app. And then it's like you give some sort of feedback to the user. And also we created an AI agent called Niraxx. Niraxx trained on all the relevant literature on PBM, and also some research literature about on Niraxx as well. And then a user can ask lots of different questions to Niraxx. Niraxx can answer as with their knowledge base. How does the system work? It's called closed loop application. Basically, with the new trend, you're going to see on the wellness market, there are lots of wearables collecting data from you and try to give you some sort of, while you try to user to understand what's going on their body and brain. But we use quite reverse engineering model, which we can get data, and also with that data, we can get some meaningful insight, and then we can send back relevant data to the brain and body to optimize it, to change it. Basically, it's more active model, let's say. You wear the headband and you stimulate the different part of the brain and body. You can stimulate a different part of the brain, your vagus nerve or your gut, and then you can see the result on the app or whatever data you collected. This is the SyncWell app, which we created. It's a prototype app. You can download it if you want to see, and you can talk with Niraxx. Niraxx would be inside. With all this research data, we created a multi-site PBM protocols, which we want to do some research. We got around 20 clinics around the world, which we are setting up some different research to understand different modulations. Like, let's say, for example, I've got anxiety. Which part of the brain do I need to stimulate? Which part of the vagus nerve do I need to stimulate? Which part of the gut do I need to stimulate? Which wavelength, how many minutes, time, and so on and so forth. And to do that, we want to create this large research setup to understand, maybe using different modalities as well, like vagus nerve stimulation, for example. There are really good research showing that ultrasound stimulation quite useful for vagus nerve stimulation. Then you can combine ultrasound with light, or for depression studies, for example, there are lots of evidence showing that TMS quite useful. Then you can combine TMS with PBM and so on and so forth to create this multimodality approach to give better outcomes. And these are all, I think, with the AI, this is going to be more useful, and we're going to see more research around that multimodalities, let's say. Again, we use same research tools, and we found that these are the PBM vagus nerve studies. As you can see, I mean, I've got this 6-7 months ago, I think, this data. Probably is much higher now around here. But in 2024, you can see like the evidence is getting there, and there are lots of publications around vagus nerve stimulation with the light or sound or electric or magnetic signals as well. Also, we we are working on to creating, multi-modality protocols for, different like mood, anxiety, PTSD, and so on and so forth. And also, this multimodality needs to be like, let's say for anxiety, which part of the brain, which part of the vagus nerve, which part of the gut, or just maybe brain and gut or wherever. These are all we are working with to create some sort of modalities around here. And there are a couple of research we use same tool and find out over here around 1,004 studies mentioning brain gut axis photomodulation, and 6 studies mentioning wavelength, and 90 studies referring application sites like places. And frequencies, obviously, mechanism and outcomes. You can use that tool to check different aspects and variables as well if you're training your AI algorithm for PBM. As I mentioned, we've got around 500 plus units beta testing. Currently, we're getting feedback from people around 20 different clinics around the world, and we want to organize this. Also, we created around 45 AI agents that will help us to create an enterprise-grade PBM protocols, which you can get, your research agent and so on and so forth to create end-to-end ecosystem with the AI. Currently, Niraxx raising a Series A investment to create more, let's say, smart wearables or smart active wears, let's say, to get data from body on brain, and then use AI to modulate, find body and brain needs, and send that signals to change and optimize body and brain. Now I'm gonna little bit pass to the second part of the presentation, which is gonna more focus, I don't know time-wise, where are we, but which I'm gonna focus on more why brain size important for AI application. As you can see on the table, neural networks and like synapse and neurons, AI people try to understand these modalities to copy them into the hardwares to machines to understand it. And you can see spiking neural networks, which is a term on AI. Neuromorphic computing people use it generally, and other like reinforcement learning using on robotics and game. And that's why I think brain science is really important for AI application, and we need more neuroscientists, PBM people on this field as well. There are a couple of discussions around biophotonic approach. I know there are a couple of people in this call as well interested into biophotonic approach and how light stimulation change the brain, what's the physics behind of it, what's the biology behind of it. But I'm going to touch in a different perspective on this. There are some cells or like neurons on the body and brain can observe the light, and then you guys all know how the PBM mechanism work. And also there are some physicists and biologists which I'm gonna touch on that base, try to understand this approach. While we are working for clinical perspective on the biophotonic approach, there are some physics and physicists or biologists, they use this approach to improve AI itself as well. But yeah, biophotonic approach basically have cells on the body and brain using light to communicate and observe the light for the change. And there are some perspective on quantum physics and classical physics as well about biophotonic approach. there are very big discussions around there as well. Most physicists agree that PBM primary mechanism is a classical physics mechanism, which energy transfer from photons to mitochondria and others, and ATP come from that, and so on and so forth. But there are some physicists and other people think that as well. There are some parts in the neurons like microtubules, mitochondria, membrane proteins, and so on and so forth. They use light to communicate, and while they are using light, there are some sort of quantum coherent superpositions involved in there as well. And I'm going to mention a couple of names later on the slides when we got more time. And one of them, which Professor Roger Penrose, which I met with him a couple of times. He's a Nobel Prize physics professor here in Oxford, and they've got a theory on quantum effect in the brain called arc theories, with a professor from Arizona University, Stephen Humbert, which I'm gonna show what's their theories talking about and how this is related to PBM. And this guy's like, I don't know, 3-4 years ago when I speak with Roger, he have no idea what's PBM. I mean, because it's a clinical application. But nowadays, especially Stuart Humbert, I saw he's very interested into ultrasound stimulation, which is again has some sort of effect on microtubules as well. The quantum people, they think that microtubules has some sort of involved on the quantum effect on the brain, and when we use light to stimulate the brain, there are some sort of quantum mechanism over there as well. Mainly, most of the quantum theories in the brain, they try to explain that with the photonic way, with the biophotons, which is understandable. And also there are different approaches as well in terms of the electrical speeds or light speeds for the information processing. And these are quite very important information for the deep tech or hardware people, like to create quantum computers or quantum chips, semiconductors. That's why this like biophotonic approach currently used by photonic researcher in physics to create photonic chips to mimic human intelligence into hardware, which is using light to process information, which will be much faster and maybe super intelligent when we got, sometimes it's going to be probably around quantum or photonic sides, because it's much faster. And also there are other opponents. They think that brain is a dark place, and quantum effects would not going to happen on that brain temperature level. But there are other people, they think differently as well. It's a big discussion in the quantum physics and physics side, but new developments showing that there are some sort of quantum processing mechanism in the brain as well. Orc theories, which is from Penrose and Hamroff, is basically focusing on microtubules and microtubules structures and component of the microtubules helping light to move from one neurons to others. And also they think that this movement happening on megahertz, terahertz, kilohertz level as well. And one neuron's got, I don't know, more than 10,000 microtubules inside. And then you got trillion neurons on the brain. And then all these microtubules synchronously working together And especially Hamrov, Professor Hamrov, he's an anesthesiologist, he's an anesthesia person, and most of his research on anesthesia, and then he find out that when they give anesthesia to the patients, they find that microtubules activation level getting down, and then they done lots of research around how this approach might explain quantum effects and collapse of the wave functions on the brain as well. These are all related to clinical side, and also at the same time for the AI, these are really important informations as well. Currently, for example, myself and our team, we are working on microtubules structure to try to mimic this model to create an semiconductor which is using quite similar architect to process information much faster, to sort energy issues on AI, which I'm going to touch a little bit later on. These are different images of the microtubules and their roles on the consciousness. And obviously there are most of the research mentioning that microtubules involve on the consciousness, and how consciousness is happening is like a synchronization of the microtubules and their communication methods, which I'm not going to go in details, but you can find Penrose and Hamrov and their ORCAC theories, and also there are other quantum physics and biophysics theories around this. The reason I put this over here to show a clinician while we are working on a clinical methods to give better services to patients. At the same time, these methods might be very helpful for AI for machine to understand human brain much better, mimic that much better, and act that much better. Also, according to Penrose, he's not thinking that AI gonna get consciousness because of if we can mimic this model into AI. But microtubule theory is very connected with the brain biology, quantum physics, and how this synchronizations of the microtubules working on kilohertz to the hertz level created this holistic consciousness, let's say. Obviously, microtubules and photobiomodulation, there are quite good research over this part as well. I've put a couple of on the reference list. I think if you are interested, you can check it. How lights affecting microtubules and the communication between the microtubules, and how this might cause some sort of quantum enlightenments or quantum mechanism, trigger some quantum mechanism on the brain as well. Quantum effects on photobiomodulation, which we mentioned. I think most of the research around the microtubules and other parts, but there are some research related to Parkinson and Alzheimer. They are more focusing on the microtubules, and they found that quite better evidence for the Alzheimer and Parkinson and microtubules' role on that. And light and sound, quite both approach, which you can reach out to microtubules to make microtubules change. And there are other theories as well, like when neurons creating energy from mitochondria. There are some theories think that there is an electrical communication, which is the classic physics theories. And there are some people, they think that there is some sort of sound communication as well. And that's why they think that ultrasound stimulation helping on that. Or there are some other theories. They think that there is a light communication as well, maybe a combination, and also chemical communication as well, obviously. And maybe combination of all synchronizedly. And this is the more most of the quantum theory guys think this synchronization as well. I think I've touched on this, like if we can mimic microtubules into a hardware, we might get light speed information processing, and this might help for quantum computers to process information much faster with less energy. I think, yeah, I'm not going to go in details. I think time-wise, we are quite late as well. I've got a couple of questions for the audience. I know they got tons of questions probably for me as well. But can we sort energy and memory information processing issues in AI with mimicking microtubules? Or the human brain uses 20-watt electric power. OpenAI's daily electric usage is 23,000 times higher than human brain, which means that if human brain with 20-watt electric process information much better, how we can use that model into hardware to make hardware less energy consumed, because with this current AI development, you're going to see people kind of having $1 trillion data centers and then a nuclear central with that because of the energy issues. Maybe the answer of that is in the brain, and we need more brain scientists to focus on the on that to solve to help the engineer to solve it as well. Google quantum processor. There are some quantum computers in the world. They can solve problem in 200 seconds, but which supercomputers gonna take 10,000 years to solve that. That's why I think these theories are around the photonic theories or biophotonic theories or microtubules or quantum effect theories are really important for humanities. If you get a quantum computer which is solving 10,000 years issues in 200 seconds, this might be really helpful for humanity to solve lots of healthcare issues and so on and so forth. And imagine you got this power into your normal laptop or your normal phone. With current technology, there is no chance because quantum needs a very low temperature. But if the quantum theories on the brain is right, then we might, if we use same model on the hardware, we might get room temperature level quantum, which you can use on your phone or on your laptop. That's why it's quite important. Brain signals can travel up to 350 miles per hour. It's like faster than any fastest car in the earth, I think. To get in AGIs, maybe using light for information processing gonna be important as well. It's like estimated to 10 bits per second. I think a couple of years ago there was a research. They calculate this 10 bits per second electrical speeds. And there are other questions continue over here, which I'm not gonna mention all of them, but most of them related to energy and information processing. I think it's like electric equal with the knowledge stuff. But yeah, I'm gonna stop share.
Thank you so much, Ali. It's quite futuristic presentation here. I will say just we'll transition to questions, but since your presentation had a fair amount of information about companies and products, I will say also have a conflict of interest as I'm a co-founder of Niraxx. With that, I will introduce a question from Marcia.
Yes, thank you very much. So I have a question. Can you please touch a little bit on the AI agents that you're building, at least a couple of them, what they do and how they are like functioning with the system that you have designed?
Yeah, we've created an AI agent model. It's called multi-agent orchestration. I used my PhD. I've done my PhD in interprofessional collaborative practice, which have other healthcare professions, they work together. And I create that model and copy that model into the machines. And we've created an orchestration agent. Under the orchestration agent, We've got researcher agent, doctor agent, and so on and so forth. Researcher agent is responsible to go to check the database, all the latest research, and get that information and send that information to the orchestration agent. And then under each sub headings, let's say agent related to photobiomodulation, agent related to depression, agent related to anxiety, which is related to PBM, and so on and so forth. We've created around 4 to 5 different AI agents which are working collaboratively when you give tasks to them, or they can automatically work as well. They can go and search, find the research, find the protocol they use it, and then check, compare with the other research and products, and then to give some sort of decision supporter for the clinician. On our case, we are currently training.
Ali,
Sorry.
sorry if I interrupt. You decide here, but we have 2 more questions. So if you want to do 1 minute answer, 1 minute question.
Let's. I mean, if the answer is okay, then let's pass the other question. Sorry.
Okay, the next question is from Cody. Briefly.
Hi, yeah, this should be quick. I'm just wondering, since you're giving people, the layperson, this Niraxx headband, if you give them any sort of recommendations on what they should be doing during their personal PBM, or if it doesn't matter.
Yes, when they got the test headband, they've got an app. On the app, we're getting their data. And then also there is an AI agent inside of the app seeing their data. And then they can ask questions directly to the AI agent, and AI agent's going to see their data and then give them feedback about their usage. Let's say if they want to do sleep protocols, then they can ask their AI agent, and AI agent's going to give sleep protocol according to their own data, basically. It's like a closed loop application.
Okay.
Yeah.
And next question is from Reza.
Hi, Ali. Thanks for your presentation. I was more interested to learn more about your AI and biosignal beside the agent of searching the platform for the research or knowledge base. Can you clarify a little bit what is your approach, what you have done so far?
For the signal processing, sorry,
Yeah.
what was it?
Yeah, for signal, for bios data.
Oh, yeah. I mean, for the biometrics data, basically we are syncing data wherever their people's devices collected now with our prototype model. But on our actual model, we want to put sensors on the top of the headband itself, using light or other sensors to get data from body and brain. Currently, we are using CNN and QNN. There are 2 different algorithm models which is cleaning data to make data ready for algorithm itself. But in the future, probably this is going to be much automatic waves. Let's say the user's going to use the headband or whatever variables they got. You're going to get data directly from there, clean it, made ready for algorithm. Algorithm going to get some meaningful answer for the user, and then send it back to the either user interface and also to the device itself.
Okay, thank you.
Right, so we've been spinning through the question. So I guess there's no question right now, but we're 1 minute. Is there any last comment or question for a minute, or otherwise we're done? All right, thank you so much, Ali. I mean, to show us a little bit the future of AI and quantum physics and PBM, they're all very interesting. And to be continued. Thank you all for being here today. Take care.
Thank you very much, guys. Thanks. Bye.